great welcome to all of you to this session on standardizing Ethernet firewall for automotive. A little bit background about ATAS and Scrypt. So actually, we were associated with the brand Scrypt before. So Scrypt has been in the industry for quite a long time. It was acquired by ATAS in 2012. So until 2021, we were still a separate legal entity. In 2022, we were doing, let's say, business under ATAS umbrella, but we still had a, let's say, the brand name Scrypt, which was being used. But from 2023 onwards, we started using the brand ATAS, and all the Scrypt solutions are offered under the ATAS brand. Some key data for ATAS. So ATAS was formed in 1994, and it's a Robert Bosch GmbH subsidiary. We have more than 2001 associates. We are located globally in 31 locations in 12 countries, and we had like a 321 million plus euros turnover before. In our product portfolio, we have multiple different product fields. So one is providing solutions in software development areas. Other is focusing on vehicle operating system. Then we have vehicle cloud services, SEC or cybersecurity. This is, let's say, the old Scrypt brand, which is part of it. And then we have DAP or data acquisition and processing solution as another product field. And then we also have an end-to-end, which offers integrated customer solutions. Focusing on today's topic, firewalling in automotive. So before we go further on how and why the standardization came into place, let's look into why it was really needed. So if we look into the trends in EE architecture, the leftmost picture is EE architecture from past. Here in this example, we see it's mostly based on CAN bus and everything is connected to each other. And this kind of architecture was not so secure, but also, I mean, it is not so fit for the future mobility. If we see the picture in middle, this is, let's say, an architecture for today for most of the OEMs or customers, but it can be also past or future for some other customers. Here in this architecture, the E architecture is based on logical restructuring. So from past to this architecture, everything was changed because of a logic behind it. And the logic was mainly based on domains. So the idea was to separate vehicles zones into different domains or different zones. And all the cross-domain communication typically went through the gateway. So the gateway always inspected if a message needs to go from one domain to another domain. And this can be valid for both CAN as well as Ethernet. One example here could be that, I mean, you have several domains like connectivity, infotainment, body, powertrain, ADAS, and whenever connectivity needs to talk to powertrain, it is going through the gateway. So this was always based on the service-oriented gateway. Here we saw more improved security solutions, but also increased bandwidth. But we also saw limited cross-domain communication. If we talk about future, or at least the idea where everyone is heading into, is zonal EE architecture. And here, the separation is not based on some logical restructuring, but it's based on physical restructuring. So we don't do the separation based on domains that, okay, this domain is catering to connectivity or infotainment, but we really look into physical place where an ECU lies. An example could be rear left, rear right, front left, front right. So this is like really the physical location of a vehicle, and that's how you segment the zone gateways or zone ECUs. The reason for doing that is, I mean, if we follow the zonal E architecture, you will have shorter vehicle wiring harness, so it saves weight and cost. In this kind of architecture, we need a high bandwidth communication link, and the main idea is that you would be reusing a lot of hardware and software, and this kind of architecture is also heading towards future software-defined vehicles. So, and the idea with software-defined vehicle is that we reuse the hardware, but for a different kind of software. Now, coming into like, there are multiple OEMs who are at different stage in the E architecture, and everyone wants to go zonal. So everyone needs a transition, but this transition is different from OEM to OEM. And this even makes it more challenging to deal with data, deal with security, deal with different challenges. So the final path, the full zonal architecture is the final aim is the same, but as we see here is every customer or every OEM is starting from a different base architecture. So reaching the final architecture requires different steps. And this also leads to some hybrid solutions. So maybe you are not able to skip some generations and directly go to full zonal E architecture. You still have a mix of zone and domain, and with time you go through it. You solve that problem. Now, we talked a lot about the challenges with respect to the new architecture, changing E architecture, etc. But as today's topic is firewall, let's start with why we need firewalls in vehicle, and maybe a differentiating factor between how firewall is different from intrusion detection. So if you see the picture on the left side, this is what a firewall does. So a message, Ethernet message in this case, gets into a system or an ECU. The firewall checks if the message is right or wrong. If it is right, it is allowed to go further. If it is wrong, it is supposed to be dropped. And in best case, an event report should be created. The picture on the right side is more talking about intrusion detection. So here, the idea is that a message gets into the system, but we inspect it in parallel to the normal message flow. So it is not blocking it. So intrusion detection system, it gets a copy of message. It is doing more pattern and behavior analysis to figure out if there is a potential intrusion or anomaly. If there is something, we report it. If not, we don't do anything. But this is not interfering with the normal message flow. Coming to why we need firewall in the vehicles, I mean, the most important requirement is fulfilling a lot of legislative requirements. Some examples, UNECE or GBT requirements in China, where they have specifically defined it for gateways, what should be done and what are the fields that should be inspected. Another reason is that we do need security. So, and if we follow the defense in depth approach, which can keep your ECU and vehicle more secure, firewall is a very, let's say, good entry checkpoint, which will basically stop unauthorized messages at the entry point in the ECU. And then from the IT world, we already know very well that if you're using Ethernet, you need a firewall. So it's very clear that now we are using Ethernet in the vehicle, we need the same on Ethernet on the vehicle side. So here in this picture, I show what are the challenges specifically come in when we move from domain-based E architecture to zonal E architecture. So if we see this transition, we see that now as the ECUs in the domain-based E architecture, as well as the function they were catering to, it's now completely distributed here and there in the zonal E architecture, because all we care about the physical location. So the domain-specific sensors and actuators may go to the zonal edge devices or could be lying centrally. Similarly, the domain functionality is handled in central compute or this vehicle computer, but also sometimes in local edges or could be distributed among the vehicle. So the connection from the edge gets translated, packed into Ethernet frames and transmitted over Ethernet backbone. So some communication is happening over CAN or some other in-vehicle communication network that needs to be transferred to Ethernet, sent to an other ECU via the central compute, and then again it needs to be translated to maybe CAN or something else. So overall, the communication is becoming really complex. Same goes with the communication policy. And everything is now getting distributed. So it's not logical, but it's based on zones. So the earlier need in the domain-based E architecture was that, okay, if we put the firewall in a central gateway, we can be fine. But that approach is not applicable anymore because the communication is also distributed everywhere. The function is distributed everywhere. So you need firewalls at different levels. Could be, I mean, the edge nodes, could be the central node. We will come into more detail in some time. And looking into this picture from a zonal E architecture, here we see the edge nodes, or let's say the end ECUs, the small ECUs. We see, let's say, zone computers, or and then we also see vehicle computer and Ethernet switch. And if we talk about firewall and IDS use cases, there are many at different levels. So if we talk about the central vehicle computer, here certain functions that can be catered by firewall and IDS could be, in the central vehicle computer, the firewall can take care of network separation using virtual LANs. It can firewall cross-domain traffic. It can firewall end-to-end traffic because there could be some Ethernet packets which are terminating in the vehicle computer, so which we can inspect there. Also, some deep packet inspection can be performed on the central vehicle computer because of resources that we have available there, and then we can also do intrusion detection there. Similarly, if we look into the Ethernet switch, Ethernet switch also has multiple use cases for firewall. I mean, in this picture, we see Ethernet switch is being used to create many domains like A, B, C, D, and E. So the network separation between those domains can be taken care by the switch with help of VLANs. Similarly, firewalling cross-domain traffic at a very high speed can be done by the switch because the switch has some hardware acceleration capability, which we can utilize to inspect packet at a higher speed. Also, the switch can perform access control for vehicle computer or vehicle server. It does not need to send everything to the central computer. Now coming to the domain controllers or zone controllers, it can perform access control and also can perform firewalling of zonal traffic. Now, if we talk about the really small end ECUs, even there we see some use cases. One example could be if a small ECU is responsible for charging electric vehicle. I mean, the communication there happens over Ethernet. It can focus on EV charging use cases. So what we see and learn from here is that the old approach of just putting a firewall in central gateway is not working because the use case is different. It's distributed, and we need to cater to all the needs. And that actually led to some of the let's say background work on why we focus on standardizing firewall. So some of the challenges that we saw with respect to firewalls on Ethernet side in the automotive world was there was no standardized way to configure a firewall. There was a high synchronization effort required between OEM, Tier 1. Configuration process was prone to error. Everyone was communicating in a different language, and it was still okay until you had to put firewall at just one place or one ECU. But now, if it will be distributed, you need to have a common language on when you talk about firewalls. Similarly, there was no harmonized connection to IDS. So at the end of the day, firewall is a security sensor, and it is generating events which are security relevant. So it would make sense if we are able to connect firewall to intrusion detection, because in intrusion detection, we have intrusion detection manager, system manager, which is standardized in AUTOSAR. So standardizing some security events will really help. Also, there was no agreed minimal set of firewall functionality. We saw requirements from different OEMs, and it was really different. Some would like to have deep packet inspection and stateful packet inspection on a lot of topics, and some were fine with just looking into very basic things. So this was also very confusing. So these all were, let's say, the key reasons why we wanted to work on this topic, and there were definitely more, but these were the few of the topics which really led to this standardization effort. So the standardization of firewall in AUTOSAR can really address all these challenges. And to really look into the AUTOSAR specific topics, I would like to hand over to my colleague, Mikkel, and he will take it over for the rest of the presentation.
Thank you. Yes, so I will now talk to you for the next minutes about our standardization activity in AUTOSAR and basically present to you what the result was of our standardization activity. First of all, brief introduction into AUTOSAR. What is AUTOSAR? AUTOSAR is a standardized middleware for automotive ECUs that comes in two variants, classic and adaptive AUTOSAR. Classic AUTOSAR is focusing on safety and real-time use cases, so it's designed to be deployed on microcontrollers, whereas adaptive AUTOSAR is more focusing on performance use cases while still providing safety to a certain extent. So adaptive is more focusing on microprocessors. I would also like to point out that adaptive, although newer, is not meant to replace classic, but both are meant to coexist next to each other, each one fulfilling their use cases. They can even coexist within one ECU, as we can see here. Here's an example of a vehicle computer architecture that hosts a microcontroller, which runs a classic platform instance, and a microprocessor that runs a hypervisor, which in turn runs several instances of different OSs. So we can see here again, one instance of classic AUTOSAR for safety use cases, two instances of adaptive. One could be for automated driving, the other one for V2X communication, for instance. And we could even have a Linux platform here for on QM level. So why use AUTOSAR to address the firewall challenges? Well, first of all, AUTOSAR is broadly used and widely accepted standard in the automotive industry. It's basically the go-to middleware for automotive ECUs. And AUTOSAR does not only provide software, but it does also provide a standardized exchange format, RXML, and tooling to configure the AUTOSAR software. And both of these, the tooling and the RXML, can also be used to configure firewalls. Third, AUTOSAR is specified within the AUTOSAR consortium, which is an industry consortium with partners from all over the automotive industry. Which means that when we are bringing now the idea of a firewall into the consortium, all the stakeholders from the automotive industry can contribute and can discuss on the features that we would like to address, such that in the end, the final solution is agreed with all stakeholders and fulfills all the needs from the automotive industry. So what have we proposed to be introduced to AUTOSAR? Well, we have proposed to introduce a firewall that, of course, fulfills firewalling use cases, so it filters incoming and outgoing communication according to a given rule set. And here we proposed basically three different layers of filtering: stateless filtering, stateful filtering. This is mostly focusing on stateful protocols like TCP, and the packet inspection on application layer protocols like SUMIP and DoIP. One of our major interests was also to introduce a standardized language for firewall filter rule configuration. I think we have just seen that in the challenges. Another feature that was important to us was that the firewall is also sensitive to vehicle states. I'll tell you more about that in some minutes. And we also wanted to have a connection to the intrusion detection system and standardize security events. With regards to applicability, I think we've just seen all the different deployment scenarios for firewalls. So keeping these in mind, both platforms, classic and adaptive AUTOSAR, are applicable for firewall standardization. However, we have decided to focus first on adaptive to have a firewall for vehicle computers and tackle firewalls for classic AUTOSAR and for switches only in a later step. Finally, I would also like to point out that the standardized language for firewall configuration, in the end, it's represented in RxML, right? Which can be read. It's just XML, which means that this configuration is not limited to configure AUTOSAR stacks, but you can also take this firewall configuration in RxML to provide a configuration for switches or non-AUTOSAR hosts, because in the end, what you need to do is to take the XML and transform it into the proprietary language of your switch, for instance, of the proprietary configuration language. But generally, the whole project was not limited just to AUTOSAR hosts, but to also cater to non-AUTOSAR hosts like switches and non-AUTOSAR based hosts. So what's the result? For this year, or for the latest release, actually, for the R2211 release, we managed to introduce a host firewall for adaptive AUTOSAR. You can see in the architecture overview that we've introduced a new functional cluster, ROFW. And I would like to take you now through a quick tour through this functional cluster, what's offered, about the architecture, about the standardized language for configuration, about the vehicle state-based packet inspection, and the connection to the IDPS ecosystem. With regards to architecture, the functional cluster firewall is a management module. So what does that mean? It means that the functional cluster firewall takes the firewall configuration from the AUTOSAR manifest and uses it to configure the underlying firewall engine. The underlying firewall engine is typically provided by the operating system, so it could be iptables in Linux, for instance, or pfilter in QNX. However, you're not limited to use to only the OS provided firewall engines. You can also use your own proprietary firewall engine if you would like to, because maybe iptables does not fulfill your use cases. ROFW does also provide two interfaces. It has one interface that can be used by applications to set the vehicle state, and the other interface is used to connect to the IDSM to raise security events. Now coming to the standardized filter rule configuration. As Sid has just sketched before, the challenge here is basically that as of today, no common firewall configuration scheme was available, which led to high efforts in harmonizing the OEM requirements with the actual firewall configuration of the firewall engine, and also that this manual translation process from OEM specifications to actual configurations is manual process, and with that also prone to errors. The idea here was that we can leverage AUTOSAR as a standard to introduce a common language for configuring firewalls. This language can then be represented within the standardized AUTOSAR format RxML, a standardized exchange format. And you can even think one step further. You can think about taking the communication matrix that you have as an OEM, run that through some tooling to directly provide allow list configurations for your firewalls based on your communication matrix that you can then represent in XML and hand over to your supplier for firewall configuration. The standardized configuration language in AUTOSAR is represented in UML. You can find that in the manifest specification. So UML is quite complex, so let's go through it step by step. So how does the language look like? First of all, what we need to define is a set of network packet patterns. So patterns that describe which values you would expect in a network packet. And when a network packet arrives, the firewall iterates through all the defined patterns. And once a pattern matches, the associated firewall action is carried out, so the network packet is allowed or blocked. The pattern can be further detailed in sub-patterns. So you can define sub-patterns for every OSI layer, for data link layer, network layer, transport layer, and application layer. And you can also define patterns for payload inspection. Additionally, for each and every pattern, you can also set a rate limit that basically limits this pattern up to a certain amount, and network packets that would exceed this rate will be blocked by the firewall. For every sub-pattern, you can then define which values you would expect to have here. So on data link layer, you can basically state expected MAC addresses, expected ether type, expected VLAN ID, and so on. On network layer, the firewall supports inspection of IPv4, IPv6, and ICMP. And again, here you can define expected values for the source and destination IP address, TTL, and basically you have access to the complete IP header and the individual fields there. On transport layer, the firewall allows you to filter on TCP and UDP. So here you can define expected port numbers, for instance. But especially on TCP, you can also filter on the stateful nature of TCP and define a maximal number of allowed connections to define a timeout for open connections. And you can also filter on the state machine of TCP by the state management based on TCP flags. So these three configuration options here are basically the stateful packet inspection part of the firewall configuration. Going to the application layer, here we support filtering on SUMIP, SUMIP SD, DDS, and DoIP. Again, you have basically access to all header fields, which on SUMIP also include service-specific values like service ID, method ID, and client ID. Furthermore, we also support length verification. So what's that? This feature describes that if you have multiple SUMIP packets within one UDP packet, the firewall compares the expected length from the UDP packet to all the combined lengths of all SUMIP packets to prevent some kind of attack here. And finally, the payload byte pattern. This allows you basically to generate generic rules. So you can define a byte value that you would expect at a given offset. And with this, you can basically define arbitrary inspection of your network packet. You can also do that multiple times, right? So you're not limited to one byte value at one offset, but you can describe multiple byte values at multiple offsets. These two parts, application layer and payload byte patterns, these are catering to the deep packet inspection use case of the firewall. Next, I would like to talk about the vehicle state dependent filtering. The challenge here is that depending on the state that the vehicle is currently in, so if it's currently driving, if it's parked, or if it's in a diagnostic state, you expect different network different network traffic within your in-vehicle network. And the firewall shall be able to adapt to this different traffic. So the firewall shall allow diagnostic communication only when the vehicle is in a diagnostic state. This is a feature that was also important to us and that we wanted to introduce to the firewall specification. So what we did is basically you are able to define a set of project-specific vehicle states and connect a set of firewall rules to these states. And then an OEM-defined application can be used to switch between these vehicle states. To be more concrete, we have here one example. We can see here that the configuration contains two sets of firewall rules, one for a driving state, one for a diagnostic session state. And we can see that the OEM's application is using the firewall state switch interface of the functional cluster firewall to set the vehicle state to the diagnostic session. So upon doing so, the functional cluster firewall will reconfigure the underlying firewall engine with the firewall rules of the diagnostic session, such that starting from here on, diagnostic communication will be allowed. I would also like to highlight here that we did not standardize which vehicle states shall exist. We have just standardized how you can define such states and how to address rules to them. But which vehicle states you would like to have, this is still left open to the OEM or to the end user, actually. Finally, connection to the IDPS ecosystem. For this, let's briefly have a look on how does intrusion detection work in automotive. First of all, what you need are some IDS sensors that are monitoring resources or network traffic and raise security events based on some given rules. Thinking one step further, you could also think about using smart sensors, so sensors that have some additional logic and that are maybe monitoring the complete network traffic on a switch, for instance. One example would be our Segregate product, and I also would say that the AUTOSAR firewall would fall into this category. What else do we need? We also need some the VSOC, a team of security experts that gets these events and analyzes them and decides about countermeasures. And of course, we need an in-vehicle distributed IDS that collects all of these security events, aggregates them, qualifies them, and forwards them to the VSOC. What's the challenge here? Well, AUTOSAR does specify parts of an IDS. So it does specify the IDSM that aggregates security events on individual ECUs, and it also does specify a set of security events. However, there are not so many, and they are not sufficient to properly analyze vehicles with respect to the network traffic. This has led to the fact that OEMs started to define their own Ethernet security events, which then in the end leads to higher efforts in the VSOC when we have non-uniform security events. We also wanted to address this challenge here within our standardization activity and provide a set of standardized network security events that can be raised by the firewall, and where we also wanted to standardize the associated context data to ease the analysis within the VSOC. So the result here was that we have introduced 15 new security events for the firewall. You can see some examples here on the right. You can see that they are basically focusing on the individual protocols that we're filtering, so on IPv4 and IPv6, for instance. And we have also some security events in addition for the additional firewall functionality, like the rate limit, for instance. We have one security events especially for this. And we have also standardized the context data that is raised together with the security events, which is the header of the respective protocol. This basically concludes what we have standardized within AUTOSAR for the R2211 release. And with this, I would like to hand back to Sid to give you some more insights on the outlook.
Thank you, Mickey. So looking into what is more to come. So as Michael mentioned that we managed to standardize firewall in for adaptive last year in 2022. So now, I mean, with this, we are addressing, let's say, vehicle computers or big ECUs with microprocessors, which are running, for example, POSIX or QNX or something similar. So that part is already addressed. But if we talk about Ethernet switches, we talk about classic AUTOSAR related ECUs like small ECUs, this topic is still open. So there are no functional specification for firewall available for switches. The standard firewall parts that we standardized in last year are still open for classic AUTOSAR, and this is something which we are still focusing on. We are working on this in this year, and we hope this will have a very good progress this year. So, so the current focus of work right now is firewall standardization for classic AUTOSAR, and the goal here is to have the same feature set as adaptive AUTOSAR, which were like filtering of network traffic, stateless, stateful, as well as deep packet inspection. Second, reusage of standardized firewall configuration language. So we want to speak in a common language. Usage of, let's say, vehicle state to apply some dynamic firewall rules. And here it could be that there are certain messages which are only allowed in certain vehicle state, for example, diagnostic mode of vehicle, but you don't want those messages to come when the vehicle is driving. So also connection of those security events raised by firewall towards IDS. The next release timeline is again R2311, so that is November this year. Coming to firewall on switches. So if we talk about the modern Ethernet switches, they have a dedicated CPU inside the switch. So the switch typically has two parts. One is the switch core or the switch hardware, where you can have some hardware acceleration features like CAM or TCAMs, which is content addressable memory, and it is like a memory where you can look into certain part of Ethernet message in one clock cycle. And then the second part is the CPU, where you can run some software. So if we talk about the CPU from the modern switches, it allows you to run AUTOSAR. So it allows reusage of existing AUTOSAR modules and leveraging AUTOSAR tooling support. So the AUTOSAR firewall specifications shall also support the deployment on switches. And as I mentioned, with respect to switches, switch deployment, there are additional features like configuration of TCAMs and other things with respect to switch hardware configuration, so that we can speed up computation, as it makes no sense to have just a software-based firewall on switch, because the main idea of running firewall on switch is the hardware acceleration. Also, extension of firewall configuration language to include TCAM rule configuration. And here, again, the next AUTOSAR release in R2311 is where we target from a timeline perspective. When it comes to ATAS, we have a product called Psychegate, and Psychegate is an Ethernet and IP firewall, and here we offer two variants. The variant on the left side is focusing on Ethernet switches. We only support certain switches, but more can be supported on porting request. And here we follow the same approach that the switch hardware or the switch core, there we do firewall pre-filters, or we call it pre-filters, and it includes TCAM related configuration, switch related hardware configuration, VLAN configuration, MAC table configuration, etc. And then on the CPU side, we run application software that can cater to needs like deep packet inspection, stateful packet inspection, or other kind of inspection, because this TCAM is very limited. You cannot do everything there, so the CPU shares the load. And in this way, it's a hardware and software co-design where the hardware assists the software to do firewalling at a high speed. The second variant is the variant on the right side, which is a plain C library, and that can be integrated to microcontrollers and microprocessors. And here, an off-the-shelf integration for QNX and Linux is already available. Some features from our product Psychegate. So basically, the firewall has a job to block illegitimate communication. So it helps you to maintain and enforce network separation with help of VLANs or virtual LANs. It offers all three kinds of firewalling schemes. If we talk from firewall term, stateless packet filter, stateful packet filter, and deep packet inspection. So the stateless packet filter is more focusing on static fields like from a packet, for example, IP address, MAC address, VLAN tag, VLAN header, ICMP related information, and other things. Stateful packet inspection is more focusing on stateful protocols like TCP, where the client and server first establish a connection and then the state of connection changes dynamically during runtime. So you need to maintain a state machine which is doing connection monitoring, and for every possible client and server. And then comes deep packet inspection, which is a vague term in automotive industry. For us, deep packet inspection is either looking into any application layer protocol or really looking into the payloads with bits and bytes. Also, Cykagate supports association of vehicle context or vehicle state to a firewall rule to offer state-aware policing. We offer denial of service protection. With help of monitoring the rate and everything, you can perform denial of service protection. And then the communication policy enforcement can be based on mainly whitelist, but also on certain cases blacklist.
In addition to the our Ethernet firewall product, we are also offering AUTOSAR security consulting. So based on our year-long experience within the AUTOSAR working group security, we have supported numerous customers on securing their communication with SecOC, on implementing security monitoring using the AUTOSAR IDSM and the AUTOSAR security events, and also in implementing the secure diagnostic security control using service 29 based on the AUTOSAR implementation in the DCM. In addition to this, we are also offering a one-day training on AUTOSAR security that contains an overview over the classic and adaptive AUTOSAR security AUTOSAR stack, including security features, where we will also deep dive into all AUTOSAR security modules like SecOC and the IDSM. So if you also have these challenges and would like to reuse AUTOSAR existing security controls, feel free to contact us. We are happy to help you here. Finally, to summarize and conclude, we have discussed today that EE architectures are changing, which comes also with an increased need for firewalls in automotive. At the same time, deployment of firewalls is oftentimes not so easy, especially when it comes to configuration. That's why we brought the firewall into AUTOSAR, first and foremost to introduce a common language for firewall configuration to ease this pain. The firewall in AUTOSAR also has additional features like, of course, stateless, stateful, and deep packet inspection. We have this use case of filtering based on the vehicle state, and we have introduced a set of standardized security events for the intrusion detection system. The specification is currently available for adaptive AUTOSAR, and for the next release, we are targeting to introduce it also for classic AUTOSAR and switches. That's all. Thank you for your attention.